All right, good morning. I am recording the lecture this morning. So remember, if you ever want that, you can go find it on my YouTube channel. Probably. I will tell you today we have lots and lots of videos. And sometimes when I upload to YouTube, sometimes I get blocked because I put on, like there's a copyright infringement or something like that on there. And so hopefully we won't have that problem. If that does happen, I can get the YouTube thing to excise it, to cut it out. But it takes time. So it takes a long time to upload it that way. Furthermore, I can send the thing to you, just the recording, and you should be able to play it on whatever video thing is on your computer. All right, so in other words, it doesn't need to be in the format of YouTube. It can be just in the recorded format. Okay, so we can try that. Did that ever work, Mallory? I sent that to you last time? No, I didn't send you the recorded last time. All right, so is that who's missing? Riley? Does anybody know Riley Eiler? Okay, I can't remember if she's in this class. Can't remember. All right, so let's get started. Y'all open your lab books to, it'll say Module 1, Part 2, Lab 2? Yeah? Lab 2, what page is that, y'all?
16.
Page 16. All right, you'll be putting your, filling in your blanks here. Chewy, you don't have a book? Where's your book, sweetie? At home,
Yeah.
but you do
Yeah,
have
I
it.
have
Chewy, you're waiting on yours?
Yeah, it's-
Okay, everybody else is good?
I don't have that yet.
You're still waiting on yours. I don't have the pictures of these. Sorry about that. All right, so let's get started. Nope, I got to do this again to use my clicker. Okay, there we go. All right, we're going to be looking at light in the sea and why does the sea look the way it does? Why is it blue? If you've been to the Texas coast, would you call that blue?
No.
More kind of a grayish green sort of a color right there. That has to do with mud that's in the water. There's mud in the water from the Mississippi River. We are on the west side of the Mississippi River, therefore we get all the mud. Has anybody been to the panhandle of Florida, where you are in the Gulf of Mexico there? It's beautiful, clear blue. It's beautiful. And that's our same Gulf of Mexico. It's just they're on the other side of the Mississippi River. So in general, if I asked you what color is the ocean, you would say? Blue, right. And we're going to see why. It turns out it appears blue because the wavelength of blue is able to penetrate deeper into the water. And I have this really fun little video. Oh wait, I have some things to fill in first. Okay, light has different wavelengths, and ocean water is most transparent to blue. In other words, it travels deeper into the water. So I believe whatever is underlined is what you're supposed to write. Is that correct? All right, so the first part of yours is written down, and all you're writing is ocean water is most transparent to blue light. The deeper the water, the other colors cannot penetrate, and bluer the ocean appears. The bluer the ocean appears as it goes down. If you've ever been to the Caribbean, it's like turquoise blue. It's gorgeous, right? Because you can see so far. It's so clear you can see far down, and the only color that's going that far down is going to be blue. There also is reflection of the blue sky. That's true. All right, so the reflection of blue sky does aid in the color of the water. Oops, I'll go back. Here we go. I'll give y'all some time to fill those blanks in. Y'all good? All right, so here we're looking at it. You see the blue is penetrating deeper into the ocean right here. Violet is too. It's penetrating fairly deeply. It's just so deep colored that it's harder to see that. All right, so we're going to watch this fun little video.
Why is the ocean blue?
Because ocean water reflects blue color of the sky.
You are right, but not completely. The main reason for oceans to be blue is the way water molecules absorb and scatter the colors of sunlight. Sunlight has 7 visible colors. They are red, orange, yellow, green, blue, indigo, and violet.
Yeah, I saw them in a rainbow.
Now, when sunlight falls on the ocean, it passes deep into the water. Here, red, orange, yellow, and green colors of sunlight are absorbed more strongly by water molecules, while blue, indigo, and violet colors are not absorbed much. Instead, they are scattered, making the ocean appear blue to us. However, as the blue shades penetrate deeper into the ocean, eventually they also get absorbed. Hence, at greater depths, the ocean is completely dark.
Yeah, it's kind of easy to understand the deeper that we go that there's no light down there, right? So it's dark, so that makes sense. And I couldn't get that sleep apnea thing off there. I couldn't figure out how to get that off there. Sorry about that. All right, so plankton also help with the color of the water. That's why some water will appear different colors because of the creatures that are living in it. All right, so different kinds of plankton will reflect light, giving off a turquoise color, and they look kind of like that. So those are living creatures, those are animals, and we will study those in much depth as we move on through our year. Now we're looking at ocean pressure. All of you know that water puts a lot of pressure on you. If you've ever been in a deep pool and you go to the bottom, it makes your ears hurt, you know, it pushes on your chest and all that kind of stuff. So for every 10 meters of depth, that's 33 feet, 1 atmosphere of pressure is added. So when we talk about an atmosphere of pressure, those of you who have taken chemistry, remember that on the surface of the Earth, we have the atmosphere pushing down on us at a rate of 1 atmosphere, it's called. It's also, I think, equal to 14.7 pounds per square inch or whatever it is. There it is, 14.7 psi at 1 atmosphere. So every 33 feet I go down, I'm adding 14.7 pounds per square inch on that pressure. Okay, so the deeper I go, the more pressure there's going to be. That's why we can't go very deeply in the ocean. Certainly with our bodies, we can't go very deep. And then if we want to go deeper, we have to get into something like a submarine. And to plumb the very deepest parts of the ocean, the submarines have to be very specially made with thick walls and thick windows, so they can withstand the pressure of the water pushing on the machine. All right. So if we're looking at it, this is sort of a schematic. Check it out. Here's at the surface, it's 1 atmosphere, so that's what we call sea level, right? So sea level is 1 atmosphere. When we go higher, like up to the mountains, and we get away from the sea level, the pressure's less. All right, that's the ears popping when you drive up a mountain kind of a sensation you get. It's a pressure change. So, but at sea level, we're at 1. You can see here. So look at the middle part here that says air volume. Notice what happens to the volume of the air in this picture right now. It gets pushed up. Just picture that kind of like a piston that's going up into a tube. Okay, so if I put it down a little deeper here at 10, it's going to go up a half. Here at 20, up a third, and a fourth, and a fifth, all the way. And notice what's happening all the way over to the right, those circles over there. Picture that being a creature, a critter's body, even your body. If you're this shape at sea level, as when you go down, you're going to be squished. All right, so humans don't squish very well. All right, when we feel that, we get very uncomfortable. One thing to help us, of course, is if we have a self-contained underwater breathing apparatus, also known as a scuba gear, then that will put pressure into you and help you a little bit. We'll see a little video on that here in just a second. So if we're looking at animals of the ocean, marine life, you can see a lot of them are going to be living up here where the pressure's not too intense, but we do have really bizarre creatures that live in the very, very deep parts of the ocean, and they have to be able to withstand that pressure. Some of them have very hard exoskeletons. We can see lobsters and things like this, and some of them are like an octopus. You can squish it. I mean, you just basically squish it. It can squeeze through little tiny, like a hole in a door or whatever, that we've done experiments with these guys underwater, so they can move their bodies around pretty freely there. All right, next video.
Sometimes, when a fish is reeled up to the surface, it will appear inflated, with its eyes bulging out of their sockets and its stomach projecting out of its mouth, as if it's been blown up like a balloon. This type of bodily damage, caused by rapid changes in pressure, is called barotrauma. Under the sea, pressure increases by 14.7 pounds per square inch for every 33-foot increase in depth. So take the yellow eye rockfish, which can live as deep as 1,800 feet, where there's over 800 pounds of pressure on every square inch. That's equivalent to the weight of a polar bear balancing on a quarter. Now, Boyle's gas law states that the volume of a gas is inversely related to pressure. So, any air-filled spaces like a rockfish's swim bladder or human lungs will compress as they descend deeper and expand as they ascend. After a fish bites a fisherman's hook and is quickly reeled up to the surface, the air in its swim bladder begins to expand. Its rapid expansion actually forces the fish's stomach out of its mouth, while the increased internal pressure pushes its eyes out of their sockets, a condition called exophthalmia. Sometimes rockfish eyes will even have a crystallized appearance from corneal emphysemas, little gas bubbles that build up inside the cornea. Thankfully, a scuba diver doesn't have a closed swim bladder to worry about. A diver can regulate pressure in her lungs by breathing out as she ascends, but must be wary of other laws of physics that are at play under the sea. Henry's law states that the amount of a gas that dissolves in a liquid is proportional to its partial pressure. The air a diver breathes is 78% nitrogen. At a higher pressure under the sea, the nitrogen from the air in a scuba tank diffuses into a diver's tissues in greater concentrations than it would on land. If the diver ascends too quickly, this built-up nitrogen can come out of solution and form microbubbles in her tissues, blood, and joints, causing decompression sickness, aka the bends. This is similar to the fizz of carbon dioxide coming out of your soda. Gas comes out of solution when the pressure is released, but for a diver, the bubbles cause severe pain and sometimes even death. Divers avoid falling victim to the bends by rising slowly and taking breaks along the way, called decompression stops, so the gas has time to diffuse back out of their tissues and to be released through their breath. Just as a diver needs decompression, for a fish to recover it needs recompression, which can be accomplished by putting it back in the sea. But that doesn't mean fish should just be tossed overboard. An inflated body will float and get scooped up by a hungry sea lion or pecked at by seagulls. There's a common myth that piercing its stomach with a needle will let air escape, allowing the fish to swim back down on its own. But that is one balloon that shouldn't be popped. To return a fish properly to its habitat, fishermen can use a descending device instead, to lower it on a fishing line and release it at the right depth. As it heads home and recompression reduces gas volume, its eyes can return to their sockets and heal, and its stomach can move back into place. This fish will live to see another day, once more free to swim, eat, reproduce, and replenish the population.
Okay, has anybody ever been scuba diving? It's really a lot of fun. I've been only about 30 feet, so I didn't have to worry about the bends at all. The bends is really only worrisome if you're going very, very deep in the ocean. All right, let's talk about the motion in the ocean. What's causing all of it to move? What causes waves and all that kind of thing? All right, first of all, we have something called global wind patterns forming something called gyres. Some people pronounce it gyres, but gyres is typically how we pronounce that. And we're going to see how that causes like swoops coming down to the planet Earth. We have something known as Coriolis effect, or Coriolis effect. If you've been in physical science, we talked about Coriolis effect. It's the spinning of the Earth. Because the Earth is rotating, that rotation is affecting the water. Just like if you stir up a bowl of water, the water will keep moving in that direction. Number 3, currents and waves. Those are usually based on temperature and wind. We have tides. Tides is based on gravity, a gravitational pull from the moon and the sun. And then we have vertical motion and overturn. This, we'll see some stuff on this. It has to do with cooler air dumping down, warmer air rising up, and there's kind of a natural overturn in the water, which is really important for animal life. This even happens in lakes and ponds and things. All right, so those are the 5 things. Is that right? Do we have another one? No. So the 5 things we're talking about when it comes to the motion and wave creation. All right, so let's talk about wind first. It's created when the sun heats the air. Okay, so the sun is shining, heats the air will begin to rise, the cold air therefore will replace it by sinking down, and that causes wind. So wind moves up and then cools and then drops back down, and the turning of the earth affects that wind direction too. So if you look at the picture over here, you can see those round circles along these little areas of the earth. That tends to be, because the equator, of course, is going to be the warmest part of the earth. The sun is hitting that directly almost all year round, and therefore that's going to heat it up, and it's going to drop it. And it's interesting how at these different levels, at 30 degrees latitude and 60 degrees latitude, then you're going to see this wind pattern. It's a very interesting wind pattern that really has to do with the temperature change plus that Coriolis, the spinning of the earth. All right, so large, mostly circular systems of surface currents are called gyres, okay, gyres. And you can see this map right here. It shows you we have these general patterns of these gyre formations. Okay, they're big circles happening, and in this map you can see, here's America, kind of on the right side here, and you can see the Atlantic Ocean has a big gyre and the Pacific Ocean has a massive gyre in it. And that's interesting. We're going to see how that affects, it actually moves things around in that little circular pattern. And sadly, one of the things that's moving around is trash. All right, so there's trash in the ocean that gets dumped there. And this big one in the Pacific right here, that most of the dumping is happening from the country of China. And it ends up swirling around in a giant mat in the middle of the Pacific Ocean called the Giant Pacific Trash Patch or something like that, which we'll get into, especially when we're talking about taking care of the planet. All right, so let's watch another video about how these gyres form.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths and are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into 2 main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted?
Okay, so notice when they said about the warming and changing that, it said those were models, based on models. In other words, that's not really happening. It's just they're thinking it could happen. So a scientific model is not the same thing as a scientific point of data. So there's no data to show that. All right, water currents. Here we go. There they are. That's what they look like. Okay, so we see our big gyres, and then we see, of course, those wind currents in various locations having to do with the temperature. All right, so here's our wind fields. It sort of showed that on that previous picture there. So winds near the surface create waves on ocean. Trade winds are what they're called. Trade winds consistently blow toward the equator. So we can see our trade winds. Yeah, the northeast trade winds and the southeast trade winds right there. And they bend to the west due to Coriolis. Westerlies are cooler because they're farther up the globe. They move from west and are unpredictable. That causes weather situations on the surface of the earth. And then polar easterlies curve the same direction as the trade winds. All right. Here we go. Is that a student?
Yeah, she's just going to the bathroom.
Oh, that was somebody leaving. didn't feel that. All right. So that's what they look like. So this is how our wind patterns are going to be. Okay, so depending on where we live on the globe, we're going to see our winds prevailing from certain places. Now, of course, the seasons also change that. Okay, so like for instance, we're entering into the fall, and some of our winds are going to now start coming from the north versus from the south. Although down here in Texas, we don't have that much trouble with that. Here's our Coriolis, though. So we live in the northern hemisphere, so our Coriolis looks like this. Now, this does affect us, mostly because we live near the Gulf of Mexico. And when a hurricane comes into the Gulf of Mexico, when it comes in, you may have noticed, so we just had a hurricane, right? What was she called? Ida? Was it called Ida? And it came in and hit New Orleans, and did y'all see where it went after it hit New Orleans? You see what it did? It curved all the way to the right, like it went to New York City. So it curved up to the right. The thing that caused it to take that right turn was the Coriolis effect, was the fact that the earth was spinning. And it took all that energy, all that moisture, and it dumped a bunch of water. I believe they had flooding, I believe in New York City itself, you know, the flooding streets and such. All right, so we're going to watch this. If you've taken physical science with me, you will have seen this. It's a great little deal about Coriolis.
In space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and the stars during the night. Every day, the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour. Well, why? Well, as you walk north or south from the equator, you're actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less, and you would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation of angular momentum. Angular momentum is the product of the mass times the velocity times the radius of a rotating object. The conservation of angular momentum tells us that for a rotating object, the product of its mass, velocity, and radius is constant for that system. Well, what does this mean? Think of a ball swinging around on a string. If you shorten the length of the string, the rotating ball spins faster. Angular momentum, however, is conserved because as you decrease the radius or the length of the string, the velocity or the rotational speed of the ball is increased so that the product of the velocity times the radius times the mass stayed the same. As an example, let's consider a ball that weighs 1 kilogram on a string that is 1.5 meters long, spinning at 5 meters per second. When we calculate the angular momentum, we find its value is 7.5. If we shorten the string, we know that the ball will spin faster. So if the radius of rotation is reduced to 1/2 meter, the rotational velocity must increase to 15 meters per second so that the product of the mass times the velocity and radius remains at 7.5. Now, how does all this apply to this parcel that we shove north? Well, as we moved it to the north, the rotational speed of the Earth will decrease. However, because the parcel of air is actually moving closer and closer to the axis of rotation, its rotational velocity must increase by the conservation of angular momentum. If you were standing at 30 degrees north and watching the parcel as it moved, it would appear to be deflected to the right. This apparent deflection is the direct result of the Coriolis force. What is really interesting is that if the parcel continues to be deflected, it would trace out a path along the Earth's surface that kept its original speed of 10 miles an hour constant with respect to the rotation of the Earth. Therefore, the path of the parcel would eventually trace out a circle, much like the path of this baseball on the merry-go-round. Watch as Amanda pushes the ball out to the center, and it makes a complete circle back to her other side. Some important facts about Coriolis force. First, the Coriolis force causes objects to deflect to the right of their intended path in the northern hemisphere, and to the left in the southern hemisphere. This is why low-pressure systems like hurricanes and extratropical cyclones circulate counterclockwise in the northern hemisphere. Second, the Coriolis force affects the direction of an object, not its speed. Third, the strength of the deflection is proportionate to the speed. For example, the faster an airplane flies, the more the pilot must adjust the flight track to account for the Coriolis force. And finally, the Coriolis force is 0 at the equator and maximum at the poles. To leave you with an interesting fact, the effects of the rotation of the Earth are negligible at very small scales. For example, if a pitcher were to throw a pitch at Wrigley Field to home plate at 100 miles an hour, the deflection of the path of the ball is very small, only about 900 microns, which is about 0.9 millimeters, or about the thickness of your fingernail. However, for an intercontinental ballistic missile, if shot a few thousand miles at 1,000 miles per hour, the deflection is hundreds of miles.
All right, so he mentioned that about a pilot having to take Coriolis into account when he's flying high and fast. And so I find that interesting. You know, you've got to adjust where you're aiming your plane, and it really makes a difference in these rockets. So if we're trying to send a rocket to the moon, we have to adjust for where everything is in the spinning of the universe, okay? All right, so moving on to waves. Oh, by the way, if we have another storm coming up, and you might say, well, there's a big hurricane coming, but it looks like it's gonna go just out to sea. That's because it's gonna make that turn, that Coriolis turn, before it ever comes to the coast of the United States. So that's why that's doing that. All right, so waves. Open ocean waves carry energy across the sea surface. They don't actually transport water. So I have, this kind of gives me pause sometimes. I kind of wonder how this actually works. We're going to watch, I think, a couple of videos that gives us an idea of what's going on here. But think about this: when you go out to the beach and you go past the breaking of the waves, like past that first sandbar or whatever, you ever notice that you're just kind of bobbing up and down, right? You're just bobbing up and down. So that's what the energy's doing. It's bobbing the water up and down. All right, and what happens is when that water bobbing up and down hits something below it, namely the beach, that's what causes waves to break, okay? And then those breaking waves, of course, move on to the beach because they're breaking forward, and they will have a tide come in and that kind of thing. So tide will bring in waves, but in general, like say we're out in the open ocean, way out in the open ocean, the waves are just going up and down, up and down, up and down, not really moving large volumes of water. Okay, so the energy's going like a wave, just like a wave. We're looking at a light wave or something. All right, so waves contain energy that is circular. We'll see a picture in a minute. The waves have the circular energy underneath it. The energy moves to the wave until it comes to a shallow water, which causes it to break. So right here, when we're looking at it bobbing up and down, we have circles of energy, circles of energy. So crest and trough, just like any other wave that we've talked about before, any kind of transverse wave. Light waves, for instance, we look at them like this. All right, so notice that energy's in those circles right there, but that's with a flat bottom. So if we bring those up to where they're going to hit something, it will break that circular energy pattern, and that will cause the circle at the top to break, and we know what breaking waves are, right? All right, here they are. So there's circle right here. Notice it's starting to cut that circle energy off, and as it moves this way, that wave, instead of staying in its regular pattern right there, it's going to come over here and end up breaking over the top right there, and then of course shallower and shallower up on the beach, you'll see that coming in as a tide, right? Okay, so shore waves act differently because the energy is in fact being interrupted by the what's happening underneath. As the water becomes more shallow, the sandy surface interrupts the circular motion. Here we have a breaking wave, and then of course that water is traveling forward into the surf zone right there. Okay, so we have our surfing waves and that kind of thing. I didn't know if you were supposed to draw this or something. Are we good? Okay, are we good? All right. So let's watch this. I like the way this one shows them just bobbing up and down.
When most people see ocean waves, like the waves you're seeing in this video from South Africa, they think that the waves carry water along with them. They do not. Waves do not transport water. They transport energy through water. If you look at the algae floating in the water, you'll get an idea of what I mean. Notice that as the wave comes through, the algae don't move forward very far. That's because the water's not really moving very far. It's moving in a circle. So as the wave passes through, the algae simply move up and then move down. Now when the waves approach the shore, something a little different happens. The water molecules are still traveling in a circle, but now the molecules that are close to the bottom rub up against the bottom. That causes friction that slows them down. The water molecules near the surface of the water don't experience that friction, so they move more quickly. Eventually, this causes the top of the wave to move in front of the bottom of the wave, causing the wave to break.
And then when it hits that bottom of that sand, in some cases it will end up dragging stuff out of that sand. That's why typically if you go beach walking in the morning, what we call beach combing, right, you'll end up finding things that were washed ashore. and it has to do with something that was close by, maybe in the sand. So you'll find some shells and various creatures or whatever who have been washed ashore. All right, tides affect sea life and wave action. It's quite amazing how the tides are so important. We don't even really think about it, but they are very important, and it has to do with the gravitational pull from the moon and the sun. So they're caused by the gravitational pull. We have two types of tides. Of course, we have something called high tide and something called low tide. We all know that. If you've been down to the coast, you've noticed that, and you can see where the high tide's been because the sand will be wet or whatever. But we also have spring tides and neap tides, N-E-A-P, neap tides. So spring tides occur when the sun and the moon are aligned, like this, what our picture is showing you right there, either with a new moon or a full moon. All right, so those spring tides will have higher high tides. There'll still be high and low tide each day, but the high tides will be higher. Okay, so you may have heard, about this. We're going to have a, exceptionally high tide. That means we're probably on a new moon or a full moon. And also you've noticed on the full moon and new moon, animal creatures included, tend to act strangely. Your dog might act funny, that kind of thing, because that pull is more. Okay, that gravitational pull is more because it's all lined up like this. All right, so the moon really does affects the tides more than the sun, but the sun has a lot to do with that, okay? But we really kind of consider what's going on with the moon. Some people wonder, well, what would happen if we didn't have the moon, if the moon were exploded or something like this? It would affect the way the tides work. We'd still have some tide action because of the sun, but it wouldn't be the same because the moon, notice, is adding to that sun, right? and the earth is going around the sun's not going around the earth, but the moon is going around the earth, causing those tides to be changed. My guess is, my hypothesis is, if we didn't have a moon, then the life in our oceans would be very, very affected. It would be terrible, right? So we need to have our moon. I think there was some point where scientists were thinking, let's try to explode the moon. I don't know why anybody would even want to think of exploding the moon, of destroying the moon. I don't know why. See, because we can do it. I don't know. But I say we need it, and so we need to have those heavy tides. And then, of course, we have our neap tides. I think I have another picture for that one. Here it is when it's at a 90-degree angle, right here. So that we have lower low tides. Lower tides are lower. We still have high tide and low tide. They're just changed by the position. And then, of course, the moon is traveling from one place to another. It takes about a full month for it to go all the way around, about 28 days. And so we're going to have, basically every day is going to be just a little bit different. And we have tides coming in, of course, at the Gulf of Mexico. Tides are really dramatic in other places in the world, like in areas that have fjords, like in Norway and stuff like this. And then we have places where the tide is negligible. I don't know if you're aware. Do you know the Mediterranean Sea? That's where Europe is, like Italy. The boot of Italy sticks down. The tide's only about 2 or 3 inches from between low and high. So they essentially say there is no tide in the Mediterranean Sea. All right, let's see.
If it weren't for the moon and the sun, there would be no tides. Now in this animation, I'm going to concentrate on the moon because its effect is the greatest. Without the moon, the waters in the ocean would be distributed rather uniformly around the Earth. But as soon as you put the moon in the picture, its gravitational force changes things. The moon pulls on the ocean water, causing it to bulge out. It also pulls on the Earth, so the Earth moves towards the moon as well. This makes the ocean water form essentially an ellipse around the Earth. So if we were looking down on the Earth, this is essentially what we would see. Now let's consider a particular point on the Earth illustrated by this house. Now remember, the Earth rotates a full revolution every 24 hours. During those 24 hours, the position of the moon doesn't change much because it takes 28 days for the moon to get around the Earth. So in the end, we can assume that the moon doesn't move very much during an entire 24-hour day. So what happens as a result of the Earth's rotation? Well, look at the house now. It's sitting in an area that has a little water, so it's experiencing low tide. As the Earth rotates, however, it starts rotating into an area with a lot of water. When it finally gets to the point where it's reached the maximum of the water, it's experiencing high tide. As the Earth continues to rotate, the house once again gets to the point where it's experiencing very little water. That's low tide. As the Earth continues to rotate, the house once again experiences an area of high water, so it's now experiencing high tide. Of course, to complete the day, the Earth would continue to rotate, putting the house back to where it experiences low tide again. Now think about what happened through the course of the day. The Earth rotated so that the house experienced 2 low tides and 2 high tides. That's why in most regions of the Earth, in most seasons, every place will experience 2 high tides and 2 low tides in a 24-hour period.
All right, so every day, too high, too low, and typically we know when it is. I mean, we know exactly what time it will be, and that's because people are, gauging where the moon is and that kind of thing. And then that, of course, the neap tide and the spring tide will come into bear on that as well. So let's say on a high tide during a spring tide, we're going to have a nice big tide twice a day. Okay. All right, so then once again, our neap tide is at a 90-degree angle. So if I asked you what's the difference between the spring tide and the neap tide, you would say the angle of the moon to the sun, whether it's 90 degrees for neap or 180 degrees for spring. Okay, on either a new or a full moon right there. All right, so I was telling you about how tides can be different in different locations. Well, in Canada, up in a place called Nova Scotia, which is in the eastern coast of Canada. It's a beautiful area right there. There is this bay called the Bay of Fundy. And the Bay of Fundy has the greatest differential between high tide and low tide. And it happens every day. Okay, so you can see right here how it's coming up into the bay right here, and then it will recede past the bay. So here it is at low tide. You see the ships right there are on the ground. And then when the high tide comes in, they're floating. This is exactly the same location at low tide and then at high tide, and I have a little video that shows it with a time, lapse. It's pretty cool. I'd like to see it. It's on my list of things to see.
Just as currents move the waters of the world ocean, so do the tides, which ebb and flow under the gravitational pull of the moon. High tides follow the moon as it orbits the Earth. Canada's Bay of Fundy on the Atlantic coast is famous for its immense tidal flow. Up to 1 trillion tons of water enter and leave the bay with each tide. Low tides empty coastal channels, leaving veins of red mud. The tides enrich the land enriches the sea. While the moon's gravity tugs.
Turnover. I was talking about turnover, how the water will change position. It happens in lakes as well, and you can see right here where we're going to have the surface is going to have a different temperature. It's going to cool it off because there's a breeze. Okay, so assuming it's a breeze is cooling the top part off, water cools quicker than land cools, and then it will. The cool water will then dump down and then replace the bottom water, which will rise up and cool. So we have this turnover right here, and you can see here we have a illustration. Some of it's just dropping straight down, but we do end up with this sort of circular motion going on. Sometimes in the hot parts of summer in Texas, we don't have that much cooling going on, so if you may have noticed, if you have a pond, sometimes the pond gets a little stagnant in the summertime. And sometimes algae just starts floating on the top, and it might even kill the pond, at that point, because of the overgrowth of the algae, because so much sunshine is on there. All right, sorry I have so many videos today, y'all. I like them. Let's watch about
cool temperatures at the ocean surface cause the surface water to become cooler. Since cooler water is more dense than warmer water, as the water cools, it begins to sink. As the water sinks, it displaces an equal volume of water in the deeper layers of the ocean, causing that water to move upwards. This process, called overturn, benefits the ocean. The surface waters are rich in oxygen. As the cool surface waters sink then, oxygen is brought to the lower parts of the ocean. The waters in the lower parts of the ocean are typically more nutrient-rich than the surface waters. So as the cooling surface waters sink and displace the lower waters, causing them to move upward, that brings nutrients up towards the surface of the ocean.
All right, so nutrient distribution is one of the big deals happening here. Furthermore, think about it. The creatures that are performing photosynthesis, they're going to be nearer the surface, right? Doesn't that make sense? What do they need to perform photosynthesis? The sun. So they're going to be near where the light will penetrate so they can do their photosynthesis, and they can distribute that stuff down. We're going to see all year long talk about different migrations that take place from the lower part of the ocean to the upper part in order to get access to food. Just like anything else, the animals in the ocean are finding strategies for survival, right? And so that survival includes getting food and getting light, getting salt, all these things that we find in the ocean. All right, here we have ocean layers, I believe. Is this something you're drawing now? Or just labeling? So the general ocean layers we have at the top, we have the surface, also known as the epipelagic zone. Epipelagic. We will have a whole module called the epipelagic zone, maybe two. Okay, so we'll spend a lot of time there because that surface layer is where a lot of life is contained, mainly because of that photosynthesis going on. Then we have something called the thermocline. The thermocline, so thermo would mean temperature, and cline would be that changing of that, all right? So guess what's going to happen as we get deeper, the water's going to get colder, all right? And then we have what's known as the deep layer, all right? The deep ocean, which is still somewhat mysterious because it's difficult for us to get down to the deep parts. We have to use very specialized machinery, submarines, things like this. We call this thing the water column. And that idea of overturn, which we just talked about the sinking and moving of the water, is important here. It's mixing that water, and we'll also look at something when the ocean does that called upwelling. So we'll get to upwelling, which is a little different process, but it is the idea of mixing the water. So all this stuff, the tides, the winds, the Coriolis, everything is mixing up the water of the oceans, okay? It's keeping it moving. So what I want you to understand is the motion in the ocean is essential for life in the ocean. All right, if we have ocean, we have energy. If we have energy, we can exchange energy, and therefore life can be perpetuated. All right, so that's important that we have this motion. We wouldn't want a still ocean. All right, it's good to have tides. All right, so as we move on through the year, we're going to be going through this water column. I think we start at the top, and we'll move down and get to those crazy creatures that live in the depths of the ocean. And when also remember, it gets colder, it gets saltier, it gets darker. And so we'll find, in fact, there are certain creatures in the depths that don't even have eyes because they don't need them because there's no light down there. Okay, some of them have really big eyes so they can catch little glimmers of light that come down that way. There's one creature that has something called a tube eye. It's almost like he's got a little, like, telescope for his eyes. It's pretty cool stuff. All right, do we have our layers? I will mention to you that when I have things like that, 1, 2, 3, right, surface layer, thermocline, deep layer, those are really good quiz questions. Hint, hint. Really good quiz questions. What 3 things are we going to talk about for layers? That kind of thing. Honestly, I can't remember what the quiz asks. I haven't seen it in 2 years, so I don't know. But understanding the water column is from the surface down to the depths. Good? All right, here it is. There is our surface layer. Goes down to about 660 feet. I don't know what the meters are in that. Sorry, does it say it on there? 200 meters? Okay, good. And then we have our thermocline, which is going to be our, drop in temperature. That's between 660 and 5,000 feet, which, where's our metric on that one? 4,000 meters. Okay, and then our deep layer, notice that we have it's our epipelagic, and then we end up with our bathypelagic, and then our down in the abyss. So the deep layer over 5,000 feet. Now keep in mind, for instance, I don't know specifically, but let's say the Gulf of Mexico is not as deep as other parts of the ocean. It may not have this part, right? Because it may end up here somewhere, because it's just a more shallow body of water. But so this is really referring to the open oceans, Atlantic, Pacific, those. It also would be a good idea to know your oceans. All right, for next week, know your oceans. All right, you may want to list those numbers, yeah? The numbers? 60 down to 5,000 and beneath 5,000. Okay, ocean motion is vital. What would happen if it were still, if there were no motion? We would have no nutrient or oxygen mixing. All right, so creatures in the ocean need oxygen. They just get the oxygen from a different place. They don't get it from the air. They get it from the water that's, the oxygen that's dissolved in the water from above. Those organisms would die. Weather patterns would be changed. It says here they would cease. I don't know about ceasing. And then plankton would die because they would create oxygen depletion. Like I said about your pond and your algae floating on the top right there, it would basically kill off stuff beneath it because it's using everything above. And that would happen too. So that's why it's important for us to have this motion. All right, what about the trash and the gyres? So we have, it's called the Great, what's it called? The Great Pacific Trash Patch or Garbage Patch or something like this. And you can see the gyre forming. Well, the trash that's floating, typically made of plastics and things like this. I have been convinced a lot by this course right here to be more mindful of how much plastic I use. So I've cut out all plastic containers at my house and things like this, and I only use glass now, and I use a cup like this instead of plastic water bottles, and just recently I started getting water in a can. So it's called Richard's Rainwater, I don't know if you've heard of it, but it's in an aluminum can, and that can be recycled more easily than plastic. So that's just me trying to be a good steward of the earth that God's given us. But if you see this right here, I will tell you, we will get into this a lot of detail about the Great Pacific Garbage Patch. And it's not like it's some people say, well, you could walk on the island of it. See, so here's people, this guy's going through a big bunch of trash. It's really more spread out than that. And in this case, if we had it like this, we could actually collect that a little more easily. We could scoop it up a little more easily with a big ship or something like this. It's actually dispersed quite a bit. And the plastic does break down. It just never breaks down all the way. So that's a problem. Okay, this is a really cool video I wanted to show y'all because we're talking about waves now. This is a guy who lives in Hawaii, who's been to Hawaii. Some people have been to Hawaii, me too, yeah. So it's great, but I don't know about you, Elijah, but you know, there's a rule in Hawaii which is never turn your back on a wave. Did they tell you that? Well, I did one time, and I thought I was goners. I really did. I was doing this in the waves, and the only thing I could think of was, oh, my poor husband's going to have to figure out a way to ship my body back to Texas. And that's why I was like, I'm never getting out of here. I'm touching the bottom, so it's not deep, but it's just like, and I'm like, oh my goodness. So I'm at the point now that when I go to Hawaii again, I'll just wave to people in the waves. It really scared me. Here we go. Let's watch this guy, though. This guy has a business with the waves.
For me, I didn't plan to be this wave photographer. I went out there because I love the shore break and I wanted to get a shot for the house, and that was pretty much it. I was there at the right time capturing pictures that nobody wanted to get involved with. People saw it, it was unique because nobody was doing it. They're shooting pipe and trying to get the cover shot for the next magazine, and that's cool, but I'd rather go out in heavy shore break with nobody out and capture some heavy four-lip monster throwing over with the sand sucking up. I have such a good time. This is Waimea Bay. This is my stomping grounds. When I was a kid, I came out here with my brother and we body surfed. And then one day I decided to get a surfboard and actually surf the shore break. Just got this killer vibe and feeling and just making it down these big shore break waves and pulling in and just getting that feeling of deep inside a tube and traveling. And it's just something I had a passion for and I still do to this day. Now with the camera instead of the surfboard, I just capture these moments. My wife came home with a picture of a wave on Waimea shore break. I'm like, honey, don't bother buying a picture. I'll go out, I'll take it. This was like 8 years ago. So I just started with a little point and shoot and taking one shot at a time. I had an SD500 and I got this thing from Amazon, 150 bucks. Put the thing in there and I took lickings. I mean, I kind of think, it thinks right before it shoots, boom, wave would go over, big shore break, boom, and finally I could time like, okay, it's right here, jacking up, hold the trigger, it'll click right when the thing comes over. Showed to my brother and my family like, wow, that's different. It was weird how it just kind of evolved. I threw my work out there, with technology, And some companies, I mean, this one in the UK, sent them my favorite 20 images, and they said, okay, we're gonna run it. I thought nothing of it. You know, we're gonna run it. I went to bed, I woke up 700 emails. Good Morning America, Today's Show, Inside Edition, all on the phone, just trying to negotiate to get me up to New York for the next morning show. I'm like, are you joking? I mean, I was like tripping out. 8 years ago, I didn't have a camera. I just love, it's just all about being on the show break and getting that shot. You ask, well, what's your settings? How did you promote yourself? Blah, 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 blah. I mean, I just went out and did what I did what I loved, and it kind of happened. I guess people feel the passion, I think, in the art, in the waves, like the backwashes, the beauty, 110%, 6 hours a day. I mean, that's my preference. So there's some dangers involved with shooting, a large show break. I mean, I've got sucked over the falls and smashed into the sand. I've separated my shoulder, had the housing bit my head, and boom, you get slapped in the face, and you get tossed up the beach, and sometimes you have a couple of friends, and you're yelling and having a girl. It's fun, dude. I mean, the worst thing for me, like the fear-wise, is just, not making it up, just wave after wave and not being able to breathe and trying to hold your breath, and another big wave's coming and you're stuck and you can't get in, you can't get out. I mean, that's the moments where I fear for my life. I don't like that, you know what I mean? It's a spooky feeling. But then you get that perfect shot, it kind of makes it worth it. I've always loved the ocean. I put in so many hours just because I enjoy it, and if I ever stop enjoying it, which I don't think I ever will, but then I can kind of step back and chill a little bit, but I'm a pretty hyper guy, and I'm ambitious and love shore break, and that's my baby,
Okay, we're gonna have a balloon between two people, so a balloon per two. Okay, so there's one of his photos. So I believe he sells these photographs, and is making a living at doing this. So if you want to be a beach bum, this is a way to make a living being a beach bum. But I don't know. If I were his wife, I'd be like, he's just being tossed around by those waves. Here's a nice one with the turtle right there. Not necessarily a wave. And then there's one of his best sellers right there with the sunset and the wave right there. Very cool. All right, here we go. We're going to start off with a balloon. We're going to be illustrating the Coriolis effect with those. So I need two people working together because you have to work together on this. And let me find Sharpie markers. Do we need another balloon? We can blow one up right here. We can blow it up. Okay, so the first thing you're going to do is use the Sharpie marker to draw an equator on your balloon, okay? I guess it'd be nice if they were more round. But basically, you're moving it. Using this top part right there as the North Pole, if you will. So draw an equator around. Got your own circle?
I can't even do that.
You need a balloon? Yeah, let me blow one up. Can you all
It's
three
a
work
line,
together?
essentially, just a line. Is it in the middle of the balloon? Oh,
Yeah, like an equator. An equator. There we go. Look, teamwork over here. I like that.
supposed to draw the equator first.
Beautiful. That's essentially what we're going to do right now, okay?
Whatever.
So honestly, y'all, I only got two safety contracts, and one of them was a repeat. So really, I only got one. Okay. All right. Okay. So now what you're gonna let me see your equators. Very good. Very good. Except for y'all. Come here. Next on. All right. So now what you're gonna do is you're gonna hold the bottom of the balloon down. Okay. And so the top round part up. So one of the group here is going to take it and hold the bottom of it and turn it. You need to be turning it. I believe we're going to turn it to the left. Okay, and have to just have it, twist it and keep moving. The second person is going to start with the marker at the North Pole and draw straight down while it's turning. Okay, you understand? So try and make it go, and then Elijah, you're just going to draw a straight line. Straight line. Keep moving to the front. So twirl. And then you're spinning. Spin to your left. That's my understanding, right? Spin to your left.
Wait, what are we doing now?
Okay, now. Okay, so after you hold it and start spinning it, and you're going to start to only draw.
Oh, wait, I'm
Our North Pole is okay. Our line. And then you're going to start at the North Pole, and you're just going to draw straight line down while she's there.
I don't know why my brain said from now.
No,
Yeah.
This is the same way we spelled it. Yeah, and it was supposed to be.
Look at our
finished
notes,
with
but
that.
Yeah, you're running this way, so now it's this way, right? No?
Okay, I'm bringing some beakers, some are larger than others.
Are you sure? Because if I was
I'll bring some smaller beakers too.
If I start here and then going down.
Okay. Well, I don't know, no, 'cause if I was spinning this way, it'd be right in there.
Alright, so this is water in here, and I have this new stuff, y'all. I'm excited about it, I've never used it, so y'all are my guinea pigs today.
Yeah. What's happening?
Y'all are getting the idea of Coriolis, yeah? Curvature that is formed from the spinning of the earth. Okay, so what I'm going to do is I'm going to bring around this fluid called rheostatic fluid. Like I said, it's new to me. We're also going to use a little food coloring. It doesn't matter what color we use, but you know, blue would be sort of ocean-like, yes. So we can put a drop in there. So once I pour it into your beaker, then you're just going to stir it. In fact, let me use one of these little cups to do that. And so what it's supposed to show you is the way that waves move. I don't know. I've never used them. We'll see. So once I put it in there, you're going to just take your spoon and just stir it around, and you should be able to see waves from. And then you drop a drop of food coloring in there, and it should help you to see it even better. Alright, so here it is. It's also known as pearl swirl. Doesn't have a... This is okay, the first one's Coriolis. That's this one with the balloon. And the second one is going to be wave action. Alright, so let's pour it out. Okay, so I'm pour this in here?
No.
And y'all are going to
It's, you know,
stir it up. Have you ever noticed sometimes if you have a shampoo or something and it's kind of pearly looking? That's this stuff they add to it to make it cool. So go ahead and stir that up, y'all. Yeah, stir that. Let me get some smaller beakers. Let's see if it makes a difference. Okay, now watch it. Now watch it. Now, okay, yeah, watch. Once you stirred it, now watch it. Watch it. Take your spoon out. Alright, do you see? Okay, you're supposed to be able to see these waves. I don't know how well it's going to work. Do you see? Do you stir it? Do you see some waves? Okay, so now we're going to add a little food color to it. Oh, do y'all have a spoon? Okay.
what is this stuff you put in?
It's like pearly stuff.
Yeah, it's pearls. It's called rheoscopic fluid.
You know, like in shampoo.
Alright, so what color do you want? You have any colors?
What's his hair?
Blue's great. Now, just put a drop in, just one drop in, and then stir again, and you should be able to, do you care? Okay. Y'all care if you have yellow? This might be the yellow that actually ends up orange. Are the Longhorn fans over here? Just one drop and then give a nice swirl to it, and you should see that color follow around. It's some sort of wave action. I don't know. We'll see. Alright. Okay, now that's good. Elsa, stop. Now, what do we see? Hey, I guess I kind of see some waves there, huh?
Why you don't use yellow?
So we'll probably use this again when we talk about, that's really pretty. What's that, red?
Red.
It looks pretty purple, doesn't it? Is that, look, oh, that looks pretty yellow. What color do y'all want? Do you care?
Blue.
Here you go. And you're going to stir it again. So let's see what it tells us in my new little deal.
Yeah, that's good.
Okay, it's a pearly white water-based suspension. Excellent for teaching ocean currents. That's where I got it. It shows turbulence and convection. Now, we're not doing convection yet because we're not talking about the heating, but if we put it onto something that heated it, you would actually see the stuff traveling to the top, which is pretty cool. We'll cover that on a different day.
You know,
Yeah.
All right.
squeeze them and they slide out like in 10 seconds.
Oh, it did say I was supposed to shake it before I put it in there. Oops. All right. Huh. I can put it in this bottle here. And shake it. This is what a Coke bottle looks like before they blow it up, right? One of those 3-liter Coke bottles. This is before it's been blown. All right, let's see how this one, I'm supposed to shake this one up, and it's supposed to full. I don't know, we'll see. You know, impressed? Alright, I guess. Okay, if I put some blue food coloring in this one. Did y'all see some waves?
Yeah.
Okay, so on this one, you're gonna actually draw maybe what you saw, some of those little wave action, okay? And draw your beaker. And then what I want in your conclusion is something about motion in the ocean and how important that is. I'm not making a mess here. I don't know, maybe you can see it on that better with the blue. So I don't know if it never really mixes together very well. You want to add a different color to the yellow? You want to put some blue in it?
Is it already turning green?
Look at some of this.
You kind of drop down, I know. All right. So you're gonna write up. Do you have a place to write up both of these, the balloon and that one? If you split, you can split it down the middle if you need to. This I can write this down. This is called rheoscopic fluid. Let me write it down. It's RH. Rheoscopic fluid, and it's supposed to illustrate the action of waves. Have you ever, when you were a little kid, made the bottle where you had the water and the oil and the bottle together and you make a wave bottle kind of like that? I think we do that in this class at some point. All right, once you write this lab up with a conclusion, we're done for the day. I would like for you to take your beaker and pour it down the sink while the water is running. It is a water-soluble stuff, this rheoscopic fluid, so it won't cause any, clogs or anything in the plumbing. But always, whenever you're dumping chemicals that are safe, you want to run the water while it's going. Okay, and also keep in mind those. If you take them to the, I'm assuming the men's room is like the ladies' room. The sinks are a little shallow. If you pour it too fast, it'll come out. So pour it slowly down there while the water's flowing. So whoever wants to take those to take care of that would be great. Leave your Sharpie markers on the table. So next week, what's happening next week?
Quiz.
Have a quiz over Module 1, and you're going to be bringing to me study guide. Also, safety contract if you didn't give that to me. I don't care about on your own. If there's questions in the book that say on your own, do that. Fill those in. But I don't need to see. Okay. You can answer those in your head if you want. I don't really care for right now. And I do want study guide.
Do we need to fill these out here, or can we fill them out?
You have till noon, so you have time to do that. If sometimes we will run out of time, if that's the case, you can always finish that at home.
Okay.
But you can be in here. Fill in.
That was
Always warn people when you're going to pop balloons. It scares people, including me. You're supposed to warn people before before you pop a balloon.
Oh, I'm
Oh,
gonna
well.
pop
I'm
it.
fixing to pop a balloon.
Thank you, Mrs. Casper.
Sleep on this for me. You are welcome. See you next week.
I can't find Sharpie. I can't find Sharpie, so I'm like, they're like.
You know, I went to go buy those and I had to show my ID.
I know, it's
And
so
I was like,
cool.
wow, okay.
Why?
I guess
Because
it's different, I guess. I don't know. I had to show my ID to buy those. Yep.
I know, they asked for an ID and we're buying some crust cake.
Zoe does that? She's so crazy. She's so silly.
There's some women in
How old do you have to
my
be?
18.
18, okay.
My sister was buying it for my dad when we were at the store.
Like
And I
the
was
kind you
just,
hang off your computer?
Yeah.
That kind of thing?
yeah, and I was with her, and so she asked my sister for an ID, and she's like, "Are you 18 too?" And I was like, "No." I'm like, "I'm not buying it."
Did they sell it to you? Because I've had.
She had an ID, so.
Yeah, I've had people with somebody was with them, wasn't it? They wouldn't sell.
I'm like, "I'm not buying it. I'm just here."
Here's your beaker.
Oh, thank you very much, appreciate that.
Mine's faster, so.
See you next week. Thanks, y'all. Oh, yeah, see you tomorrow. Got water for you. Thank you, Audrey, appreciate that.
Bye, Miss Casper.
Bye, sweetheart. See you later, have a good week. Thank you, I appreciate that. We got this. Take it. Here.
The study guide's in the big book, right?
In the textbook, yes,
Yeah.
at the end of the module, you'll see probably 20 questions or something along that line.
Okay.
You can print them out, you can write them out, and you can skip number 1, which is
Okay.
all the definition.
Do we need to write what the question was and then the answer? Or
Just do it, like a complete sentence and I'll understand. Mostly I'm just making sure you did it. I'm not grading it. Where did I put-
Where would you like this spoon?
You can leave it on the table, hon, I'll come pick it up.
Okay. And balloon in the corner?
Yes, thank you.
Thank you, Miss Casper.
You're welcome, Charlotte, I'll see you next week, hon.
You're good.
Here.
Thank you, appreciate that. Oops, sorry about not stopping the